All right, so Brittany, for step one, what's the product of step one?
So it's going to be the same skeletal structure that OH has, but instead of OH being there, wouldn't it be just be BR?
Yes. So that's that PBr3 is a way to convert alcohols into alkyl halides, right? So we're gonna do that first. And the reason I wanted to do it this way is to make it kind of applicable, right? It's one thing to just do the reactions on paper, but then if you're actually doing this in a lab, you're making each one of these intermediates, and then you need to take an NMR, infrared, and all that to confirm it. So the first product should look like this. That's step one. Somebody from room two, what's the product from step two? If I take that alkyl halide that I made in step one and stir with magnesium metal.
You're just gonna get you're gonna swap that. It's gonna be the alkyl halide plus the BRMG.
So to be this,
Yeah.
right? It's
Right.
what type of reaction is that?
A Grignard.
Granular. It's the granular synthesis. Now, for the granular, it's really difficult to study those by NMR unless you run that reaction in like a sealed tube, a sealed NMR tube, and you can monitor it that way. Because that granular, once you expose it to air, it's a wrap. Uh, so the first step was an alcohol to alkyl halide. Second step was a granular synthesis. All right. Somebody from room 4. What happens when I take the granular and react it with benzaldehyde? What am I going to get from that? So I have a granular,
If
I have a aldehyde. Go ahead.
if nobody wants to go from that group, I can try to answer.
Go ahead.
So it just be the ring with the MGBR sticking out, right?
Okay, let's think about it now. This is so here's your granular. Remember the carbon in the granular is nucleophile, right? It's partially negative, and then magnesium is partially. So the granular is a nucleophile, and then I'm going to add that to an aldehyde. Remember this little mnemonic I gave you? Granular plus an aldehyde or ketone equals an alcohol, right? So you have benzaldehyde, and then you quench it with some type of proton source. You should get this. I gotta move this up. Hold up, or shrink it. All right, so you should get this. OH. Make sure I got enough carbon. 1, 2, 3, 4. Yeah. So that's the product from that step. All right, because you took a granular and then you added it to an aldehyde, and that should give you an alcohol. Well, actually, and I don't think I showed I should have put benzaldehyde, then H plus. That'll give me an alcohol. Otherwise, it'll just be uh, an alkoxide with a magnesium on oxygen. All right, so that's that. The last step we haven't covered yet. We're going to cover carbonyl synthesis on starting next week. But that last step is the Swern oxidation. It is let me put that over there. The Swern oxidation is a way to convert alcohols into carbonyls. Right. So if it's a secondary alcohol, you're going to oxidize it to a ketone. Right. So the final product is going to look like this. Right, that's my final product. This is after the Swern oxidation. and the swirling is like I think it's oxalochloride and DMSO. It's the one of the stinkiest reactions you could ever do because it's working with sulfur. So I've done this before. It'll have the whole lab smelling like rotten eggs, but it works though, and it's very efficient reaction. So we got basically the NMRs, the gradient. We don't have an NMR for that, but I think we got 4 spectra down here. 1, 2, got 3 spectra. So we're gonna look at spectrum A, and then spectrum B, and then spectrum C. We're going to try to match up those products to one of the spectrums. So let's look at not all the products, just the alcohol, the ketone, and the alkyl halide. So this alcohol right here. So we're going to try to match up this one, and this one, and this one. All right. So right away, so for spectrum A, what can we rule out for spectrum A? Based on the presence of these protons right here. What type of protons show up in that region between 7 and 8?
Wouldn't we normally look at a structure to compare?
We know, yeah, but we should know at this point, like the ranges where aromatic protons show up, where vinyl protons show up, where alkyl protons show up, where protons next to our sp2 carbon show up. Like that, you don't need a structure to know that information. From 7 to 8 is aromatics. Right, so aromatic protons show up in that region. And we got 2 spectra with aromatic protons showing up here and here. All right, because you got the same protons here. So those 2 spectra immediately are going to correspond to either this product right here. I'm going to copy them and paste them. It's going to be either, hold up. Sloppy. 1 second to drag this down here. So it's going to be this product or it's going to be the alcohol. It's going to be one of those 2. Which one do you think it is? Now we got some infrared information down here too. Right here. What do you think?
Okay, so the first one should be more downfield. So wait, is that what you're asking? Like which signals correspond to the molecules?
No, not at the moment. I'm asking which one of these two compounds. Let's try to rule one of them out.
I think you ruled the alcohol out.
Okay, why do you say, you're right? I think you're right. Why do you say that?
Oh, well, according to the IR spectrum, alcohol would be around 3,200 through 3,400, and that's just 3,000.
Put your, you hear me clapping? Put your cash app in the chat so I can buy you lunch today. You're absolutely right. The infrared does not indicate the existence of an alcohol. because the infrared stretch for alcohol is about 3,300, somewhere up in there, right? But the 3,000 and 2980, what do you think? What stretch is that? We've seen that, right? If we don't have the infrared, but it's like if we see that 3,000, 2980 and it's jagged looking, what does that normally represent?
OH, I think.
It's
Is it
the
an alkyl?
it's the alkyl stretching. Good. So we're gonna go with this one. And there's another infrared stretch right here that gives it away, right? That's my ketone stretch. That 1760 is my ketone. So that's a way that we can use the two processes, the infrared and NMR in tandem, to kind of solve the structure. Now we got to go in and figure out what's what. So we know now that it's this ketone that this spectrum represents. So now let's go in and put the hydrogens in and see what's non-equivalent. And this doesn't have any symmetry, right? Well, the chain doesn't. So all of these are going to be non-equivalent. So we're going to put hydrogens here. Come on, Russell. Hydrogens here. And then that's a CH3 right there. All right. And then, of course, you have your aromatics. And here you can see this is going to be easier to pick out what's equivalent and what's not equivalent. Actually, let's do the aromatic part first. So you see the three signals down there, but you actually have 5 aromatic protons. So that means that there's some equivalence. So we can look at these two, and then we can look at these two being equivalent, and then this one being non-equivalent to those, the rest of them. So that's why you see those 3 signals. So let me see, one of those is going to be a doublet. And I think it's going to be the green ones. That's the doublet. And then both of the other two would be, let's see. That pink one is also going to be a triplet, because if you look at the pink, it has a neighbor on each side. So we're going to call that a triplet. So I'm going to say it's this one right here. Oh, wrong pen. So that's that. And then the blue one we're going to put right here. And again, the aromatics, you get like kind of weird coupling because of you can rotate around this bond and get rotational isomers. So we're going to call that. All right. Now let's look at the chain. How many signals are going to be present for that chain?
4.
4 signals. Good. Very good. Let's start with the methyl group. What do you think that's going to be? Furthest upfield, furthest downfield? What do you think?
Upfield.
Upfield. Good. Closer to 0. So and what would the splitting pattern be for that methyl group? It's going to be a doublet, triplet, quartet. It's going to be a triplet. And you can see down here, you have a triplet. Let me go through my whole little spectrum of colors. You have a triplet right here. There's no integration on here, but that triplet corresponds to this CH3 right here because it's got 2 neighbors. All right. There's another triplet on the spectrum. What do you think?
It's the protons next to the carbonyl ring.
Good. The protons that are right here. Let me get some different colors. Right here. These protons, right? Why are they showing up at what is that? 3. Why are they showing up that far downfield?
You said why they're downfield?
Mm-hmm.
Because they're adjacent to a carbonyl.
Good. They're adjacent to an sp2 carbon. That's exactly right. Now, 2 in the middle, which ones do you want to do? You want to do the ones closer to the CH3, or you want to do the other 2?
We can do the ones close to the CH3.
All Let's do that. So right here, what should that signal look like? Should it be a doublet, triplet?
Sextet.
Should be a sextet. So let's look down here and see if we see one. Right? Which one of those two signals is a sextet?
The one next to the CH3.
To the further to the right, further upfield, right? So right here, you can see 1, 2, 3, 4, 5, 6 lines in that signal. One of my dots. I need to move. Sorry about that. All right, so that's 6 lines in that signal, and we're gonna color that. That's too close to the other one. We'll color it right there. All right, good. This is good. All right, now what about the other set? Let me change that color too.
It's gonna be a pentet.
Pentet. Right, it's going to be a pentet because it has 4 neighbors, and there's only one signal left to resolve. resolve, excuse me, and it's here. It's a pentet. All right, so that's all those are. I tried to color code it so we could see them. All right, that pentet is at about 1.4, something like that. All right, any questions about that? Right, can you see how the synthetic part and then the spectroscopic part go together, right? You can do synthesis all day, but if you have no way to confirm what you made, then it's kind of pointless. Okay, and then think about how people like Percy Julian, who was a notable African American chemist. Think about how people like him had to do chemistry, right? They were using different tests because there was really not a spectroscopic method available to them when they first started working. So they had to do a whole bunch of other tests. As a matter of fact, he came in under fire because there was I think it was a British chemist who synthesized a molecule, did a total synthesis, and Percy Julian came back and did it and disproved the other guy's synthesis. He said that it wasn't correct because he did a particular test at the end where he confirmed his structure, and then it was different from what was published. So he caught a lot of flack for that because who are you, little black man, to tell me that I'm wrong? But hey, it is what it is. Let's go ahead and do the other aromatic structure since we already got it. If you never heard of Percy Julian, you need to read about him. He's pretty awesome guy. And a good not a good chemist, a great chemist. Let me crop that X out. He actually patented a synthesis for an anti-rheumatoid arthritis drug. And when the American suppliers wouldn't work with him, he started working with a supplier in Mexico and bringing in the starting material was derived from like a plant, some type of plant. I can't remember the name of it. But anyway, he started his own company. When his suppliers wouldn't work with him, he started his own company. And when they wouldn't ship to him, he started contracting out in Mexico and South America, having that plant grown down there. And then actually, I think he opened a plant in Mexico, and so he could synthesize this drug and import it to the United States. So yeah, he's a phenomenal guy. Had his house burned down, and I think he was living in Chicago at the time because he was the only black person that could afford a house in his neighborhood. They burned his house down. Yep. And when he ended up, his first job interview was in Wisconsin, Appleton, Wisconsin. I think he went to work for DuPont. It was either DuPont or one of those companies. And the fact that he was there but couldn't. He got that day before he was supposed to interview and couldn't spend the night. He ended up working for a different company, and he revolutionized that company. So the initial, it was either DuPont or it was another big uh, chemical company. It was like a gigantic company, but you couldn't be in Appleton, Wisconsin after dark if you were black. So he left and he ended up at a different company and developed a whole bunch of different processes for them, made them really rich. Yeah. So you should definitely check him out. Anyway, all right, let's go back to here and see what we got. So we got a proton here. We got two here, two here, two here, and a CH3 here. Right? We can already go, we know that CH3 at the end of the chain is going to be a triplet. That's not going to change, right? The only new proton that we have to consider is this one right here. But we'll come back to that. And you can see down here, that's all the aromatics are kind of showing up under one signal. So we're just going to leave that and we'll just call it aromatic. All right, so the triplet for that CH3 is going to be
Upfield.
upfield, right? All the way down here. You can see it right here. All right. What about that? The triplet down here. What about this one? What do you think? Look where it is. It's remember the
Is it going to be the one connected to the alcohol?
yep. That remember we call those carbonyl protons. And it does not split with the OH, but it'll split with the group next to it. So that should be a triplet. And the chemical shift is exactly where it should be for a carbonyl, somewhere between 3.5 to 4.5, somewhere in that range. All right. What this little ugly peak right here, that's going to be my OH proton. Notice it doesn't split, but it's sometimes you see it, sometimes you don't. It's really poorly resolved proton unless you got a really strong magnet. So that's that. Sorry, wrong pen. All right. What about here? Let's do these protons right here. What about here?
Will those be a quartet?
It's a quartet. That's exactly right. You got one neighbor on the right, two on the left, N is 3, and plus 1 will be 4. So it's going to be right. Let me change the color on that. It's going to be right here. And that's that quartet is going to correspond to, let's see, can fix that. These protons right here. Good. The other two protons are going to be tough to resolve because in this NMR, you can see how everything is kind of overlapping. And that happens sometimes. When you have, sometimes you have protons that where the signals overlap like that. But let's just say for the sake of argument, let's just do these right here. What should the split, at least let's see what the splitting pattern should be. What should that be? Split into?
A pentet.
Pentet, good. And then here, what about here?
A sextet.
Mm-hmm. So those two protons are going to be in here somewhere. They just kind of overlap, and this is a crappy, this is actually a simulated spectrum. But both of those protons are going to be in here. What color did I get with that pentet? Purple. So both of them will be in here. All right. Hopefully that helps. We are running out of time. I think we could do the last one though, because it's just the bromide here. All right. So you can see right away you're gonna have 1, 2, 4 signals. All right. And this is, again, you're gonna have a triplet, 2 triplets, a sextet, and a pentet. Right? Which triplet, and then we're gonna end with this, which triplet would be furthest downfield?
The one closest to the BR, so the protons next to the BR.
Right here. And then this triplet here will be upfield, because that's got 2 neighbors also. That's gonna be this one. The other 2 you can see, right? You see one of them is a pentet. There's 5 lines right there, and then one is a sextet. All right, so this one would be a pentet. Go ahead and color them. So that's that. And then the sextet would be here. Same color. Sextet would be here, right? So that's that. That's how we apply NMR, infrared. We didn't talk about mass spec, but that's how we apply these techniques to synthetic problems. We do a synthesis, and then we take the NMR, and then we go through the NMR and resolve it that way. So we got to stop here because it's 9:59, and I'm going to upload this to the notes section in Blackboard. And let me get this cache out. Yeah, that was a clutch, Andy. Nice work. All right. Any
Thank you.
questions? Yeah, no problem. Any questions before we log out?
Yeah.
Go ahead.
All right. So Dr. Russell is Pierce.
Mhm.
I was crippled, right? I'm technically still crippled, but I'm trying to make up all my work.
All right. We could talk after this. I got another class at
Okay.
10. I'll be free after that.
Okay.
All right. No problem. All right. Anything else? All right. Y'all have a good weekend. I'll see you on Monday.